Welcome everybody to the second lecture of our machine learning course. Today I'm going to show you clustering methods, actually just two, k-means and DBSCAN. So let's say we have given a data set without any labels. And the, the data points here are living in a two-dimensional feature space. Dimension 1 is called x1 and dimension 2 is called x2. Now, our task here really is today to find subsets of data that kind of look similar. And the problem here is, well, we don't have any labels. So this first cluster may correspond to, I don't know, that species of dogs with those pointy ears and the brown fur, and that cluster here may correspond to white dogs, but we don't really know because we don't have any labels. Could also be that this is a cluster of dogs with blue background, and this cluster is of images of dogs on grass or on green background. And also no labels means we don't really know from the beginning on how many of these clusters are there. That's something we want to maybe derive from the data itself. So let's introduce the clustering problem more formally. So we have given a set of points, and again we use the capital X here, as a set of vectors in m-dimensional vector space. We have given a distance metric d, so typically that could just be the Euclidean distance or L2 norm. So our goal, our objective here is to group points into clusters of neighboring points. So we have to assign each of these points exactly one cluster, C1 through CK, such that the union of all these cluster sets is X, our data set X. And the neighborhood here is really determined by the distance metric D. And that's also something very interesting we'll see in a second. So since we do not have any target labels, yi, this is an unsupervised problem. Okay, so before we introduce a new algorithm to you, I wanted to go through this example with you to emphasize the importance of the distance metric or the importance of how you represent your input data. So let's say we've given this data set here of dog images, and now depending on how we have represented these images, remember last lecture we said, okay, we could measure the size of the salmon or the sea basses, and we could, I don't know, take the color of the fur and so on. So depending on what features are important, you kind of implicitly define what kind of clusters you're looking for. So let's, for example, think of two clusters that my algorithm here found. Here, for example, this cluster could correspond to dogs showing their right body side, and while examples in this cluster here all look directly into the camera. Could also be done quite differently. For example, here this cluster would correspond to white fur, and these bodies here have brown fur. So the similarity between those samples really goes down to the question of how we represent the data, or what kind of features the distance metric has access to. Before starting with this new algorithm I wanted to introduce you to, let's think back to last lecture. We introduced you to an algorithm used for classification. So we had labels for the data, those colors here. And k-nearest neighbors classified an incoming unknown point by looking at the distances to all points in the data set. And then, for example, this guy here would have been classified by a 3 nearest neighbor classifier as a green point because 2 of the nearest neighbors were green. And I'm mentioning this because KNN is really one of the few algorithms that use the data itself as a model of the underlying problem. Most algorithms and most lectures that will come up in the future introduce you to a way of modeling the data. Yeah? And the algorithm that I'm going to show you today uses a very simple model of the data to represent clusters. So meet k-means, that's an algorithm that already tells you what this model looks like. So we have k-many means, so arithmetic means, averages of our clusters. So although we do not have any labels of the data, we represent the clusters and therefore divide the data set into k-many groups using cluster representatives or centroids. Yeah. So these representatives are really the means of the cluster that they represent. So for our data set X and the cluster centers C, we use our centroids mu1 through mu k. So these are those stars here. And the optimization objective, so the goal that we want to fulfill is that we want to minimize this expression. So what does this mean? Well, we iterate over all the k clusters, and within each cluster we look at all these points in a cluster and compute the distance to the cluster center, to the centroid, mu I. And we sum up all these distances and sum all these all those intra-cluster distances over all clusters, and that's our global optimization objective. And we hope, and you'll see that's the case, that is a good objective. So if this is minimized, the clustering is optimal. So to give you an intuition of what this objective quantifies, I have moved those cluster representatives to a place that I wouldn't say is optimal. Yeah. So for example, the yellow cluster sits in between those point clouds and represents data points also here. Yeah. And this blue cluster representative represents only these 4 points here, and the green one sits in the middle here and represents this cluster and also this part of the middle cluster. And so looking at our objective, we would sum up all these distances to all the green points plus all the distances from the points here to the blue representative, and all the yellow points add their distances to their yellow centroid to this sum. Yeah. So, well, we haven't calculated this, and I can't tell you what the actual distance is. What we want is to move these such that in the end this this sum is minimal. Yeah? So how does it work? Well, first step, we need to find a starting point for the centroids. So what we do is we take our K clusters and say they're empty. Yeah? So we have not yet assigned any points to them yet. And then we take the respective centroids and put them somewhere in the data space. Yeah. So we could think of, looking at the region that the data actually occupies, and then within this cube, let's say, we would randomly sample with a uniform prior 3 locations or K locations. Yeah. What we also could do, we could just randomly pick 3 data points and take them as a starting point for our centroids, mu I. So the next step now is to assign data points to those centroids. And remember, each data point has to be assigned to only one of these clusters. Yeah. So what we do is we iterate over all the points in the data and compute their distance to each of these K clusters. Yeah. So in the end, we have a matrix, let's say, for all the data points and all the K centroids. And in this matrix, we'll find the value for the distance metric of all the points to all the centroids. And then what we do, of course, we look for the minimal distance and then look at which of these cluster centroids was closest, and then assign the point to this cluster. So let's look at it again for this one example point here. So we measure these 3 distances, and then obviously the point would be assigned to the green cluster. And then of course we have to do this for all the points, and then this would be our intermediate cluster labeling. Yeah. So all these points belong to the green cluster, all these points to the blue cluster, and only 2 will be assigned to the yellow one. Now, the next step is to update the centroids. So given a set of points, remember, those cluster centroids are supposed to be centroids, are supposed to be the mean of this point cloud, of this set of points. So what we do in every time step, is we compute the centroids as just the sum of all these points within the cluster, and then divide this by the number of points, which is just the classic average here. Yeah. Okay. So this configuration here is then the intermediate result of an iterative process. So we will now repeat the assignment step 2, and the update step 3. So this is what it then looks like in the next step. We have assigned a number of new points to the yellow cluster, for example, and then we move in the center again, and so gradually those centroids will hopefully arrive at their final location. Now the question is when to stop. And obviously we should stop when nothing's really changing anymore. Yeah? So if for all the clusters. So yeah, for all I, so for all indices of 1 to k, the difference, so really the distance, using the distance metric d, of the current and the last cluster center is smaller than a given epsilon. So again, this is a hyperparameter. You have to play around a little bit to find a good thing, a good value. Doesn't necessarily have to be 0, or we don't have to need those clusters to be the same in each iteration or after each iteration. It needs to, it is sufficient to have a small epsilon here. So small changes don't really matter. Yeah. Now the question is, what if, because I don't know, the data is arranged weirdly, what if the centroids keep moving indefinitely? Yeah. So this could mean that maybe your your epsilon is too small. So those centroids may move a little bit back and forth, and it could or would be sufficient to stop. But it could also mean that those steps of the cluster centers are really big, and that's because the data is arranged weirdly, and then you can't really find a solution here. So obviously one of the solutions to handle this situation is to stop when you reach a certain number of iterations. So let's sum up. K-means is really an algorithm that fits on one slide. So the basic idea here is to minimize the within cluster variance over our cluster. So the distance of all the points to the cluster center within a cluster summed up over all clusters should be minimized. And we initialize by randomly choosing cluster centers. And then we repeat these two steps. First, we assign points to these clusters, and then we update the cluster centers to represent those data points correctly. And we do this until we converge or we reach a time limit. Now, let's discuss a little bit how the initialization of the cluster centers may lead to favorable or not so favorable end results. Yeah. So since this is an iterative approach, we do this, starting from a given configuration to certain stop configuration. We might not find the optimal solution because the start values were not optimal in this case. Yeah. So for example, think of one cluster being assigned to a single point that is a little far off the data distribution, and then one of the remaining k-1 centers has to now represent a larger cluster, and that's not a globally, let's say, optimal solution, but that's the solution the algorithm finds given a certain initialization. So what can you do about it? Well, you just run multiple initializations and save them, and then compare them and take the best solution. And so what is the best solution? Well, like I said earlier, we look for the global optimum so that the distances within the cluster of all points to the cluster centers summed up over all clusters is minimal. Another question is how to choose the k. Well, sometimes you know how many different clusters you expect by looking at the data, which could be interpreted as some kind of label, right? And this obviously knowledge should be used, but sometimes you don't have it, or sometimes you don't want to impose this kind of bias onto the process. Yeah? So what you could do is you use a lot of cluster centers. Yeah? And well, in the limit, you cannot use more cluster centers than data points that you have. But that obviously isn't something that you want to do, because this will lead to an overfitting of the data. Yeah. And also using the optimization objective won't really help here. Yeah. You can't minimize this varying your k, because you will end up using a very, very large k overfitting to the data, and then your objective is 0. Yeah. So that's something that we don't want to do. So how do we choose k? So obviously the solution is something between k equals 1, which in itself is a solution that we don't really want, because this would be just the mean of the data, and this value is the sum of all distances to the data to their mean. And we don't want to be here, because this is an overfitting. Yeah. So what we want to do is we want to increase k and decrease the loss, and stop increasing k if the gain in loss, so the amount of how much we get better, is smaller than a certain threshold tau here. And again, another hyperparameter, what this tau is depends on your data, depends on your distance metric, and so you have to optimize this parameter as well. Let's come to a couple of problems here. The world isn't perfect, so the data will have noise, and k-means, and every mean, every average, especially the ones that we use, are to some degree susceptible to noise. So let's look at this cluster here. This mean is somehow drawn away by this one outlier, and so probably a better representative would lie more here in this direction. Yeah. But what you could think of is that adding another cluster for some noise processes may even give you the chance of detecting those noise clusters. Yeah. Another problem is that we are modeling the data distributions, the cluster distributions, as spheres, as spherical distributions, because the only thing that we know is that they have a center. Yeah. And we don't care about if they have some shape. We implicitly expect them to be close to a spherical shape. Yeah? And so this is a common example. Let's think of two clusters, ring-like clusters, and one is contained in the other. K-means won't be able to detect these guys. So this was k-means. A very simple algorithm, I would say, and the good thing is it's still broadly in use. Yeah? And one of your assignments will be to implement this, see if you can get it to work with a couple of data sets that we will give you, play around with the hyperparameters, and visualize your results. We are slowly leaving the introductory side of this lecture and move more deeply into a little more complex algorithms like the next one. So the next algorithm is called DBSCAN. There's nothing to scan here. It's derived from the title of a paper that's called Density-Based Spatial Clustering of Applications with Noise. And it's really a cool algorithm. It's not that more complex than k-means. So the basic idea here is that we, give me a second, laser pointer. So, the basic idea here is that whatever cluster we have, it's the result of an underlying process of, creating the data, right? Whether that's sensor reading or some measurement process of a human. Anyway, it's there's an underlying distribution that tells us how likely or how frequent certain measurements or observations are. And this underlying distribution doesn't have to necessarily be a Gaussian like here. But our observation here is that those points that are in the center of this cluster or this distribution are in a dense neighborhood. Yeah? So they lie in a dense part of the distribution. So density means in a certain neighborhood they have more points than points would have in a low density region. Like, for example, those that are still within the distribution, but maybe on the border. Yeah. So if the cluster is or if you leave the cluster, well, then the density is lowered for once, because there are no points behind the border. Yeah. So it doesn't necessarily have to be such a smooth transition into low density areas. It could also be, just a box density here, and then the density on the border is low because there's no point or no probability beyond the border. And then we have outliers, and we don't want these to include in the cluster anyway. So so the idea behind DBSCAN is use the density or estimate the density of the points, identify points that are in the core of a distribution, identify points that are in the border area of a distribution, and identify points that are neither, and throw away these and store these and assign them to a cluster. So this is a one-dimensional distribution, and this idea works even in high dimensions or in higher dimensional spaces. So, for example, we have this let's say worm-like or like sausage-like distribution, and you see that the core points here are really in much denser areas. So those points are a little transparent, so the greener the area is, the more overlaps there are, right? So indicating a higher density, and towards the borders there's really nothing, and then there's some outliers that we don't really want to include here. So this is how the algorithm works. We have two parameters to the algorithm, or hyperparameters. I think towards the end of the video I will explain what the difference is between parameters and hyperparameters. Just think of preset values that the algorithm takes and uses in its execution to obtain those clusters. We have two of those. One is called the radius, and one is the density. And this is how they are going to be used. So let's assume we have these couple of points here, x0 through x6, I think, yes. And you see already that there are some points that have higher density and some that have lower density. And now, to estimate the density in an area, we look at the neighborhood of a point x and collect all these points into a set. Yeah. So n of x0, so the neighborhood of x0 is the point itself because it's inside this area, and then all these other points. And with this parameter eps here, we have some way of adapting to different kinds of data. So some may be sparser, some may be denser, and that may be relevant for the clustering process. So this is a parameter that we can tune to see how this ends up in different clusters. So, so with the neighborhood function, we get a number, or we get a set of samples. Now, a core point now is a point that has at least min points many neighbors, yeah, in the set of its neighbors. So x0 here, for example, is definitely a core point. It has 1, 2, 3, 4, 5 points. So that's at least 4. So that's a core point. Border points now are those that are not themselves core points, but they do have core points in the neighborhood. So for example, x6 here has 3 points in its neighborhood itself, x6, x0 and x4, and x0 is a core point, so that makes x6 a border point. Yeah. And those guys that we really don't care about are the outliers or noise points, and they are neither a core point nor a border point. So for x5, for example, there's no point in its neighborhood, and so we disregard x5 as a noise point. So how do we compute this for not just one cluster, but for an unknown number of clusters? And the algorithm that I'm going to describe to you here is given in the original paper. There are a couple of variants out there. Think, for example, of a two-pass algorithm. So you first go through all the data points and classify those who are border points, and then you go again through all the data points and look if they have a core point in their neighborhood, and then you can classify them as borders, and then you assign or you cluster them in the respective clusters. But there's a little more complex and I think a better, nicer algorithm for you. And the idea is also not very hard to understand. So we only look at points that haven't been yet visited. So we run through all those points in the dataset and look at those that we haven't yet visited and classify them to be either a core point or not. Yeah? So not means they could either be a noise point or a border point. And for the core points, we look at their neighborhood. So every point in the neighborhood of a core point is at least a border point. Could also be a core point. Yeah? And those core points, those are the special ones we want to keep them in a set so we can look for their neighbors and for their neighbors and so on. And the algorithm in a step-by-step fashion is like this. So in pseudocode, yeah, for every sample x in our dataset, capital X, look if they have been visited. So if the label of x is something, then get a new x. Yeah? Otherwise, we'll continue here. So continue means we will continue the loop. Yeah? But if the label is undefined, so it wasn't visited, we will continue here with this code. and look for the neighbors. So n is the set of neighbors of x within the epsilon. And if the number of samples within this neighborhood is smaller than our threshold, then x is a border or noise point. Yeah? So we assign it a label that's called noise here, and we'll continue in taking the next x. Yeah? Otherwise, so the number of samples within n is larger or equal min points, then x is a core point. Yeah? So x is a core point, and we have a counter c that's just an integer that gives you an ID of the cluster, and we assign a new cluster ID to the label of x. So if a point has a number or an ID as its label, it is assigned to a cluster. We don't really explicitly store whether it's a core or a border point. We just keep it in our set of points for a given cluster. And for the subsequent steps, we define a so-called seed set, so a set of points S, and we assign it all the neighbors except x itself. And for every y, so all data points in the seed set, we ask if this label is noise. So if the node has been visited, which indicates it is a is a noise point or a border point, but since it's in the neighborhood of x, it cannot be a noise point, it's a border point. Yeah? So we assign the point y a label that corresponds to the same label as x, so it's part of the same cluster. Now, if the label of y is defined either because of the previous step or because we visited it before and assigned it to some other cluster, we do not continue. We get a new y from the seed set. So, but otherwise, so if the label is undefined, so we haven't yet visited it, we surely can say it's in the neighborhood of the core point, so it does belong to the cluster of x. And now we will have a look at the neighborhood of y, compute this neighborhood, see if y is a core point, so if the neighborhood size is larger than our threshold, and if so, we will put the neighborhood into the set S and continue with the loop. Yeah? So this way, for a given cluster that we have visited, we'll go through all the core points and assign also identities to the border points. And if we do not have any more, then we'll go up and get a new point from the dataset X and continue. Yeah. So I hope this was intuitive, and you see the algorithm isn't that long. There's a couple lines of code, and you will be able to implement that, no problem. So a few words with respect to runtime. So the neighborhood or neighbors function, range query, can be accelerated by using some way of indexing the data, sorting the data. So for example, using some kind of tree structure. And this brings the complexity down to the complexity, linear complexity. And so co-op points really are labeled exactly once. So in the pseudocode one slide before, you will see that we'll throw away any point that we have that has a label other than undefined or noise. Border points are labeled at most twice, and noise points are labeled exactly once. I hope you believe me. Maybe we should ask you why that is in the assignment. But I think an important thing is that you remember that the runtime complexity is n log n on average. So to summarize, we've compared we've introduced you to k-means and DBSCAN, and by the way, there are loads and loads of other clustering algorithms that all have their advantages and disadvantages. But comparing those two that we had, DBSCAN defines what noise is. So k-means doesn't really care. A data point is a data point, and so DBSCAN is less susceptible to distortions of the clusters that are due to outliers. Yeah? And also, k-means can end up in different results in different clusterings depending on how you initialize the clusters. And that's not the case with DBSCAN. Also, for example, in the first row of this this figure here, you see two clusters, at least I would identify them as clusters of this circular shape. And k-means cannot identify those, but rather divides the distribution of data into two parts that do not correspond to those circles, but DBSCAN can. Yeah. It has reliable bounds on runtime, so it's better than k-means. And well, that's a little subjective, but it uses intuitive hyperparameters, so the radius EPS and the minimum number of points within this neighborhood that identifies core points. Yeah? Can be guessed and computed from data processing, but that's the case for the k and k-means as well. Although really we do not have to define anything that relates to the number of clusters in DBSCAN. So k-means, for example, could cluster those two point clouds into one cluster. DBSCAN correctly identifies these. So that's it for this video. These were k-means and DBSCAN, two famous clustering algorithms. I hope you enjoyed the video. I hope you collected a couple of questions that I'd be happy to answer next Monday. Take care, stay safe, goodbye.